G'day and welcome back to McGrathematics for our final video in the proof topic for extension 2. We're starting off with a flashback from earlier lessons. We have 4 statements here. X and Y are whole numbers, so which of these 4 is true and which 3 are incorrect statements? Pause the video, give them a read and decide on which one you think is the true statement. Okay, well done if you had a read of B and you said, you know what, that makes sense because question B is saying, or option B, sorry, is saying, for any integer, there exists an integer where if you square the original number, you get an integer. So if we translate that into English, it's basically saying if you take an integer and you square it, the result is an integer, which is always true. So option B is correct. A, C, and D are not always correct. So that's why we're going to go for B. Well done if you said the same thing. All right, for our final video for 2021, we are looking at inequalities in mathematical proof. Now, heads up, I do find these questions personally very challenging. So if you feel like you're not getting good at these right away, don't feel bad because it took me quite a while and many hours of practice before I got to a point where I'm like, you know what, I'm not terrible at these, but I still have some room for improvement. All right, let's start off with some inequality properties that we're going to be using today throughout our proofs. So most of these seem really mundane, but we're going to be applying them in ways that are a bit less mundane, which you'll see later on. Okay, first point is saying that if A is larger than B and B is larger than C, then this of course means that A is also larger than C. Makes sense? And if A is greater than B and B is a positive number, that means that A times B and B squared, well, we're essentially taking this inequality and we're multiplying both sides by B. Because B is positive, this sign doesn't turn around, so we get AB is greater than B squared. For the third point, we have A is bigger than B, which are both positive, and C is greater than D, which are also both positive. Now what we can do here is we can actually multiply these inequalities together and say that A times C will be bigger than B times D. Okay, you can only do that when you know that both sides of the inequality are positive. All right, for the fourth one, we have A is larger than B is larger than 0. So what does that tell you about 1 over A and 1 over B? If we think about a simple example, 3 is greater than 2, but 1/3 is less than 1/2. So if you have an inequality where both sides are positive, if you take the reciprocal, the sign is going to turn around. Okay, next one, fairly obvious. The absolute value of A is always going to be greater than or equal to A. If A is positive, they'll be equal to. If A is negative, then the absolute value of A will be positive, and thus it'll be larger. And for the next one, pretty similar, we have if A squared is greater than or equal to B squared, this means that the size of A, or the absolute value of A, is greater than or equal to the size of B. And the last one, we already explored in an earlier lesson, which you may be familiar with. This is called the triangle inequality. We have that the absolute value of X plus the absolute value of Y is always greater than or equal to the absolute value of X plus Y. And if you think about X plus Y in terms of vectors, it'll be hopefully obvious to see why this is always true. All right, some other useful facts we'll be using throughout this lesson to help us in our proofs are that A plus B is just a number. So A plus B squared is always going to be greater than or equal to 0 because it's a square number. Likewise for A minus B squared. Doesn't matter what's inside this bracket, as long as you're squaring it, you're always going to be greater than or equal to 0. And last useful fact is that if A is greater than B and A and B are both greater than 0, it means that the square root of A is greater than the square root of B. What this means is if we have an inequality where both sides are positive, we can take the square root of both sides and the inequality sign doesn't turn around. That's very useful. All right, let's dive into some examples of how we use inequality proofs. Here are our first ones, some milder ones to warm up. We have X and Y are positive numbers. First one is prove that X squared plus Y squared is greater than or equal to 2XY. Now for beginners, my main 2 tips when you're starting inequalities like this is step 1 is if there's any fractions, try and get rid of them because that should make your inequality much easier to work with. Second tip is that usually you want to put everything on one side of the inequality and so you're comparing against 0. That's what we're going to do first in question A. We're going to pull this 2xy across to the left-hand side so we have minus 2xy. Now we're trying to show the left-hand side is greater than or equal to 0. Luckily, x squared minus 2xy plus y squared should be familiar to you as a perfect square expansion. So we could factorize the left-hand side as x minus y all squared. Now, this is great news because we know x minus y is a number, so we know x minus y squared is greater than or equal to 0. This means we can start our proof with this last line and say, hey, I know this is true, which means if I expand it, I know this is true. I can add the 2xy across the other side, and there we have the target as required. Okay, so the way I've answered it in blue is not typically how you want to write your proofs. You want to, if possible, start with a statement that you know is true and then work towards the target that you're trying to prove. Okay, so the blue writing I'd be doing on my scrap paper. The red writing I'd be putting in my writing booklet to actually answer the question. Okay, having a look at question B, like I said, if we can get rid of the fractions, this should be a bit more approachable and easy to see how we're going to prove this. So we're going to multiply each individual term of this inequality by x to the 4, y to the 4. Because we know x to the 4 and y to the 4 are going to be positive, the sign doesn't need to turn around, so we're all good. Now our fractions simplify to y to the 4 plus x to the 4 greater than or equal to 2x squared y squared. Now this kind of looks like what we proved in part A, except instead of x and y, the base letters are x squared and y squared. So it's going to be a similar proof to what we did here in red, except instead of x minus y squared, we just need to do x squared minus y squared squared. Okay, so recognizing that, we would be starting with this last line in blue. We would be expanding it out to get this line. We would add the 2x squared y squared across, and then we would divide everything by x to the 4, y to the 4. That's going to get us back to our original target. So this is the direction in which we'd write our proof, go from what we know is true to what we are trying to prove is true as required. Okay, so it does kind of feel like you're answering questions backwards at times, and it does take a bit of getting used to, but that's the beauty of inequalities. Okay, up next, we have a famous inequality that's called the arithmetic mean geometric mean inequality. On the left-hand side, we are taking the arithmetic mean of two numbers, which is adding them together and dividing it by 2, like you've been doing since year 8 statistics. On the right-hand side is a different type of average, which is called the geometric mean. So for this one, you multiply the two numbers together and you get the square root. It's going to get you a similar number, except this statement is telling us that the arithmetic mean is always greater than or equal to the geometric mean. Let's see if we can prove it. All right, let's start by pulling the root AB across the left-hand side. Like I said, always useful to have everything on the left-hand side comparing against 0. Now we'll get rid of this fraction by multiplying both objects by 2. So we get a plus b minus 2 root AB greater than or equal to 0. If we rewrite this left-hand side in this form, a minus 2 root AB plus b greater than or equal to 0, you might recognize this as similar to what we were working with before, where normally we had a squared minus 2ab plus b squared. We have that identity, except instead of a squared and b squared, we have a, b, and the square roots of a and b. What that tells me is if we go back to our original starting point in the earlier questions, and instead of doing a minus b squared, if we do root a minus root b squared, if we expand out this left-hand side, we get this line here in blue, and then we're all good. So we start with that. We start with root a minus root b squared. Expanding that out, we're going to add the 2 root ab across to the right-hand side, divide both sides by 2, and there we have our target. So like I said, once you realize where your starting point is, that's where we start it, and we work towards the goal in proper mathematical fashion. All right, epic, on to the next one. All right, for part A, we are trying to prove that for a, b, and c, which are real numbers, they are positive real numbers in fact, a over b plus b over a is greater than or equal to 2. All right, like I said last time, if we get rid of this, if we sort of rearrange this expression without fractions, hopefully that's going to be more simple for us to work with. So let's have a go. Let's start off by multiplying everything by ab. So we get a squared b on b, ab squared on a, and on the right hand side we have 2ab. These fractions simplify to a and b, so we have a squared here and b squared here. While we're at it, we may as well pull the 2ab across the left hand side, and then what do you know, we have our expansion of a minus b all squared once again. So as I mentioned, a lot of these questions do just rely on the fact that a minus b squared is a positive number. So we start with that fact and we write up to the target in this direction. So we're starting with a minus b squared greater than or equal to 0, expand it out, add the 2ab across the other side, and then divide everything by ab, and we end up with the target we were trying to prove. All right, now hopefully that's going to be a useful fact in proving part B, where we have A plus B plus C outside of the reciprocal sum together greater than or equal to 9. All right, let's have a think about this one. First thing we're going to do is just expand it out and see what happens. Okay, that's what this blue line here is. We're multiplying everything by A. So we get A over B, A over C. Then multiplying everything by B, and then multiplying everything by C gets us this full expression. Okay, the reason we did that is because we're trying to apply part A, where we have A over B plus B over A is greater than or equal to 2. Also conveniently, we have A over A, we have B over B, and we have C over C, and they're of course going to be 1. So rewriting this, we have the 1's all grouped together. I'm going to put the A over B next to the B over A, B over C next to C over B, etc. The reason I've done this is because in part A, we proved that A over B plus B over A is greater than or equal to 2. With similar logic, we can show that B over C plus C over B is also greater than or equal to 2. So in our expansion, we have 3 bits of algebra that we know are all greater than or equal to 2, and then we're adding 3 to it. So 2 plus 2 plus 2 plus 3 makes the 9. So that's how we're going to prove it. Okay, we use the fact that we're quoting from part A. We know this is greater than or equal to 2. So we can say, well, then these 3 plus together, we've got the same thing essentially, just with different letters 3 times. So these guys are going to be greater than or equal to 6. If we add the 3 1s in, we get greater than or equal to 9. Okay, so starting with part A, repeating that 3 times to get greater than or equal to 6, adding in the 3 plus 1s, and then we could have our line at the top here in blue, which then gets factorized to the original target. So we have proven the statement. All right, some hectic algebra for us. Good fun. Moving on to example 4. Again, this one is very challenging in terms of algebra. Our approach is going to be very similar. We're going to chuck everything on the left-hand side and see if we can explain why that is greater than or equal to 0. If you like a challenge, by all means, dive in before I spoil it for you. Okay, here we go. So bringing the a plus b cubed over 4 over to the left-hand side. Now, getting rid of the fractions, as always, by multiplying every individual term by 4. Okay, now what we're going to do is we are going to expand out a plus b cubed using a binomial expansion, and then see what we can do with what's left over. So in brackets here is our expansion of a plus b cubed, which hopefully you're familiar with that from extension 1. We're going to times everything by -1 to expand it. And in doing so, we'll have 4a cubed, take away a cubed, so we get 3a cubed. Likewise, we get 4b cubed, take away b cubed, so we get 3b cubed. Okay, now on the left-hand side, it's difficult to compare things that are adding and subtracting when you're trying to show greater than or equal to 0. Usually it's easier to show things if they are multiplying. That's why our goal for this question now is we are going to attempt to factorize the left-hand side, because with an expression like this, when it's factorized and you have multiplication rather than addition, it's going to be easier to explain why you are greater than or equal to 0. So what we can do is we can divide everything by 3 to simplify our terms. So we just have a cubed, b cubed, and the rest. Now we're going to group the a cubed with the a squared b, and then we'll have the ab squared with the b cubed. The reason I've written them in this way is because now this is going to make our factorizing, which we're going to use grouping in pairs factorization. In this form, it'll be a bit easier. So out of the front 2 terms, I'm going to factor out an a squared. So we get a minus b left over inside the bracket. For the second pair, I'm going to factor out a negative b squared. So we're left with a inside, and then negative b squared out of positive b cubed is negative b. This is good because in both the front and back section of the inequality, we have an a minus b that we can factor out. So we have a minus b outside of a squared minus b squared. Again, this is more good news because a squared minus b squared is a difference of 2 squares. So we can factorize this once again. Okay, now we end up with 2 a minus b terms that we can group together as a minus b squared. Now, this stage that we're up right here, this is going to be much easier to explain why this is greater than or equal to 0. We know a minus b squared is greater than or equal to 0 because it's a number being squared. We've gone over that many times. Now we know that a and b are greater than 0, so they are positive numbers. So it's not a massive stretch of the imagination to say that a plus b is also positive. So what we're left here is a positive number multiplied by a positive number, which we know is always going to be positive. Okay, so we can explain why this last line here is positive using a product rule, which means that all the lines above it are also going to be true until we get back to our target. Okay, so once we've figured this out, we start with a statement here and explain why this is positive. We expand it, and then we work our way all the way back up to the target, which is right here. Okay, moving on to the next one. Example 5, we have A, B, and C are positive numbers. First thing we want to show is A plus B is greater than or equal to 2 root AB. We've already proven a very similar inequality like this earlier in the video, so I encourage you to pause the video and see if you can prove this one by yourself now, because it's very similar to example 2. All right, let's have a look. So all we need to do is recognize that this is an arithmetic mean compared with a geometric mean. So we can start off with the square root of A minus the square root of B all squared. We know this is a number, so it's greater than or equal to 0. We expand it out and we get A minus 2 root AB plus square root of B squared, which is just B. Now we just add the 2 root AB across, and there is our target as required. Okay, so quite often you'll have inequality questions set up like this, where part A is relatively easy, and then you use that to make part B a bit more doable. So in part B, we have hence or otherwise show that A plus B times B plus C times A plus C is greater than or equal to 8ABC. So looking at part A, we have some information about A plus B. We know this is greater than or equal to 2 root AB. What we're going to do now is set up 2 more inequalities that we can use, except instead of using A and B, we'll use B and C, and then we'll use A and C. So we know this in red from part A. We can then say, well, that means that B plus C is going to be greater than or equal to 2 root BC. And similarly, A plus C is going to be greater than or equal to 2 root AC. Okay, so sometimes you'll need to prove an inequality and then sort of create multiple versions of this inequality using different letters if you need to. Now what we can do is multiply these 3 inequalities together to get A plus B times B plus C times A plus C. So multiplying the left-hand sides together, so we must also multiply the right-hand sides together. Now this is good because 2 times 2 times 2 is 8, and we get the square root of A times A, B times B, and C times C. So we get A squared, B squared, C squared. All right, good news here is that we have the square root of A, B, C all being squared. So this square root and these square terms are going to essentially nullify each other, leaving us with 8ABC, which was the target in the question. So there you go. The painful truth with inequality questions is that if you pick the right starting point, you can often get there very quickly, but sometimes it does take a bit of trial and error to get from where you are given to where you're trying to go. It takes practice. It's very frustrating at first. Okay, for example 6, a bit more of a spicy one. We have A, B, C are greater than 0. Prove that A squared plus B squared plus C squared is greater than or equal to AB plus BC plus AC. All right, well, let's have a think. First of all, we know from the very first example today, we know that A squared plus B squared is greater than or equal to 2AB. Okay, this is how we proved that before, starting with our A minus B squared, expanding, and then adding the 2AB across. So we know this is true, but we want to have an extra C squared in here, and we want to have ABs and BCs and ACs involved. Okay, that tells me we need more versions of this inequality that also involve C. So from this, we're going to write another 2 pairs of inequalities. We're going to have B squared plus C squared is greater than or equal to 2BC. Okay, so we have our BC term. We also need one with an AC term. So we'll do A squared plus C squared is greater than or equal to 2AC. Okay, so I knew to do this because I know I needed an AB, a BC, and an AC, and I knew this identity here, so I'm just sort of making 2 duplicate versions using different letters. Okay, what we'll do from here is we are going to add together these 3 inequalities. So we end up with A squared plus B squared plus B squared plus C squared, etc. is equal to 2AB plus 2BC plus 2AC. All right, this is great because on the left-hand side, we have 2A squareds, we have 2B squareds, and we have 2C squareds, like this. Now we can just divide by the common factor of 2, and we end up with the target we were trying to prove. A squared plus B squared plus C squared is greater than or equal to AB, BC, and AC. And we've already answered this in the correct direction because we've started with what we know is true. We've made 2 duplicates, added them together, and we have our target. Absolute poetry. Now let's see if we can use that to, in part B, prove that if a plus b plus c is equal to 1, so we know that, then prove that AB plus BC plus AC, so the right-hand side, is less than or equal to 1/3. Okay, so we know we need to use part A, so we need to get some A squareds, B squareds, and C squareds involved. Now we know A plus B plus C is 1, so this is good because it means that A plus B plus C squared is going to be 1 squared, which is still 1. All right, cool. Let's expand out this bracket. Okay, you can write A plus B plus C multiplied by A plus B plus C. Once you do that full expansion and collect all your like terms, you should be looking at this expression. A squared plus B squared plus C squared plus 2AB, 2AC, and 2BC is equal to 1. Now we have an equality, we have equal to 1. We really want to have an inequality because we want less than 1/3. Okay, here's where it gets a little bit tricky. What we're going to do is we're going to use the fact that, well, if A squared plus B squared plus C squared is greater than or equal to AB plus BC plus AC. That means in this equality line here, if we rewrote this, but instead of having the A squared, B squared, and C squared, if we change them to AB, BC, and AC, that means we have made this expression smaller. Okay, because A squared, B squared, and C squared are larger than AB, BC, AC. So if we substitute these values, we haven't got the same thing. It's not going to be equal to 1. It's going to be less than 1. Okay, that's how we incorporate part A into our proof, by making the substitution and changing it from an equals 1 to a less than 1. This is good because we have like terms that we can group together. So we get 3AB, 3BC, and 3AC. Now we can divide everything by 3. So on the left, we get AB plus BC plus AC. And on the right, we get 1 divided by 3. So there is our target. That was the trick, being able to start with your A plus B plus C squared, expand it out, and then use the information from part A to form your own inequality that you need to get the target. But yeah, pretty challenging for me at least. All right, finishing off this nonsense with an HSC question that I find this question very challenging. Every time I try to do it, I always get stuck at some point. Let's see if I can make it through unscathed today. Okay, they've already told us that the square root of xy is less than or equal to x plus y over 2, which is good because I've already proved that twice today, and they are giving it to us for free. Okay, from that, prove that the square root of xy is less than or equal to the square root of x squared plus y squared over 2. X and y are positive and real. If the examples in this video made sense, by all means, hit pause. Part I is pretty doable. Part 2 is where things get really challenging into the band 5 type questions. Okay, here we go for part I. First thing we can do is take our inequality and square both sides to get rid of those pesky square root signs. Okay, already looks much more achievable. Now we can just multiply the 2 across to get 2xy. If we subtract 2xy from both sides, we're going to end up with x squared minus 2xy plus y squared is greater than or equal to 0. And just swapping it around so we have everything on the left where we like it. Okay, so with a quick bit of algebra, we end up with x squared minus 2xy plus y squared, which we know is the expansion of x minus y all squared. We know that is true, so everything above it must also be true. So we're going to write our proof from this last blue line up to the target for our 1 mark. All right, now hopefully that's going to be an important feature in proving part 2, which is the cube root of ABCD less than or equal to the square root of the sum of the squares divided by 4. Once again, A, B, C, D are all positive and real. Okay, here we go. So we're using part I, except instead of X's and Y's, we clearly want to be using A's and B's and C's and D's for part 2. So we know that root AB is less than or equal to root A squared plus B squared divided by 2. We can set up similar inequalities for CD. So we have the whole gang here, A, B, and CD. Now we want to get A, B, C, D together. So what we're going to do next is multiply these two inequalities together. So we have root AB times root CD is less than or equal to these two guys multiplied together. Combining the square roots, we get the square root of ABCD is less than or equal to the square root of this guy multiplied by this guy. Okay, here's where things get gnarly. Now we are going to use the information in the question, which was that the square root of something times something is less than or equal to the sum of the somethings divided by 2. That's what we're going to apply with this square root sign just here. We have the square root of this times this. So we can say that this expression is less than these guys squared, these guys plus together and divided by 2. Okay, so we're applying the inequality from the question that they gave to us, which we didn't need to prove. Square root of this times this is less than or equal to this plus this divided by 2. Okay, that's the key to this question, because now up top we'll get a squared plus b squared plus c squared plus d squared over 2 over 2. So that fraction will sink down and make a squared plus b squared plus c squared plus d squared all over 4. Now we can get from this to the target, which we're trying to get for 2 marks, by just taking the square root of both sides. Okay, when you take the square root of a square root, you end up with the 4th root. On the right hand side, we have the square root of the expression as required. So if you manage to get that by yourself, you're doing amazing, because I wouldn't have got that. But yeah, there is a challenging level of HSC question on inequalities, in case you were wondering. All right, that'll do it for today's video. Hopefully some of that was vaguely helpful, but yeah, these are tough, so sorry if I didn't nail the explanations. All right, cheers for watching. I'll catch you guys later, probably. Cheers, bye.